So I'm Tom van Goedem, and I will be talking about a new type of timing attacks, namely browser-based timing attacks. So first a bit about myself. So I'm a PhD student at the University of Leuven, where I conduct research on the security and privacy of the web. And in my current research, I'm focusing on side channel attacks in the browser. I try to call myself a hacker, security researcher, and a CTF player, uh, because I'm very much interested in security, and I play CTFs with my university's team called Hacknam Style. Yeah, you can also find me online with my blog or on Twitter. So in this presentation, I will first give an introduction into timing attacks, which are a type of side channel attack. So a side channel attack means that you don't observe the information directly, but you use some information from the environment to infer secret or private information. These attacks are not new. They've been known for decades. But the main focus for timing attacks and side channel attacks was or is still a bit in cryptography. So in cryptography, the attacker tries to retrieve the cryptographic key, or for instance, exploit secure connections with the Lucky 13 attack, for instance. I will come back to this in a bit more detail later on. So the concept of timing attacks is pretty straightforward. So first you perform an action, so you do something, and then you measure the time, how long it takes to do this. So you measure you start your timer at the start and you stop your timer at the end. And then you analyze or compare this timing measurement with a measurement that you obtained before, or just because you know things about the system. And that's the timing attack. So last week I came up with a new type of timing attack, namely the drunkenness timing attack. And in this type of timing attack, you try to determine whether a person is drunk or not. So what you do is you slap a person in the face, and then you measure the time from the time you slap him in the face until they slap you back. And if this time interval is short, then it probably means that the person is not drunk, and if it takes a long time, then this person is drunk. But of course, I like to do experiments with attacks. So I asked a friend of mine, can I perform a timing attack on you? And he agreed. Well, he wanted to stay anonymous, but that didn't happen. So he's called Matthias, and we want to determine whether Matthias is drunk. So for this, I go to Matthias and I slap him in the face. And at this point, we start our timer. And it happens until he slaps me back. And he slaps me back quite fast, so in a bit over 3 seconds. So is Matthias drunk? Well, probably not. But of course, we don't have any other timing measurements to compare this with. So my experiment had a second part. And for this, I needed to know the state of Matthias. So I needed him to be drunk so I can compare the two timing measurements. So I gave him a lot of good Belgian beer. And after a while, I was quite certain that he was drunk. So then I did the same timing attack. So I went to him and I slap him in the face. And again, this is when I start my timer. And as you can see, well, he has trouble getting up, and it takes a while before he slaps me back. So to come back to the question, is Matthias drunk? Well, yes. And that's because, well, the timing measurement that we obtained in the second part, it's, well, much larger than in the first part. So basically, this is the key concept of timing attacks. Well, we can compare it to other types of timing attacks. So in the drunkenness timing attack, the response time of the victim is related to the drunkenness of his drunkenness. And the same applies to recovering a cryptographic key. So there we measure the execution time, and if a certain bit of the key is 1, it will take a longer or shorter time versus when the bit is 0. The same thing also happened with Lucky 13, the attack. So there, the user was, the attacker received a TLS error message based on whether the padding was correct of the TLS message. And that would allow the attacker to determine the plain text of the information. And then, there's the web-based time attacks, and I will go into a bit more detail into those. So these are also not very new. They have been known since the year 2000, which is, in the web standards, a very long time. So to compare, to give a comparison, the cookies are only implemented into the browsers in 1995. So 5 years after that, timing attacks were developed. So that's a very long time ago. And more recently, there were other types of timing attacks in the browser. So there was the Pixel Perfect attack by Paul Stone. And there, the rendering time of the GPU was found to be related to the color of the pixel. So that would allow an attacker to read out the pixels from an iframe. So, so basically you have your iframe and then you apply SVG or CSS filters. And based on, so for instance, if the pixel is white, then it would take a long time. And if the pixel was black, it would take a very short time. And that would allow you to, read out all kind of secret information from a web page. Another interesting attack that was also found 3 years ago was one by Eduardo Vela, named Sir Darkcat. And he found that execution time in JavaScript was related to the input of an attacker combined with some secret data. So by sending a lot of post messages, it was possible to infer the secret data. And then, so these were pretty devastating attacks, but the main focus of my talk will be on another type of time attack, namely the ones that were invented by Borts and Bonnet in 2007, and they're called the direct timing attack and the cross-site timing attack. So I'll first briefly explain what the direct timing attack is. So on the left-hand side, you have the attacker, and the attacker is directly attacking a web server. And this web server, has like a login page, and when the login happens with a post request, for instance, the server will check the username and password. So the attacker sends post requests, and the server, well, looks up the row where the Batman user is, and he checks the password. And the checking of the password goes from, well, left to right. So he first checks whether A equals B, and well, that's not correct. So he sends back an error message, and the attacker sees this error message at 2.5 seconds. So in the next step of the attack, the attacker tries, instead of AAA, he tries BAA. So then, well, the B is correct, and then the server checks the A, which is not correct. But because, well, it takes two comparisons, well, for the server, you can see that the time is larger. So that allows the attacker to know that the first letter of the word was a B. And then he can keep on doing that, and eventually he will retrieve the password of the Batman user. So these attacks, they kind of work, but they have a lot of limitations. So any irregularity on the network, so a bit of lag on the network, it messes up the complete attack because, well, these comparisons, they take like microseconds, and well, the jitter on the network, it might be in terms of milliseconds. And well, of course, a web server is not used by a single person, but by multiple users at once. But recently, people have developed well, solutions for this. So new types of attacks that allows them to still well, create an attack. So a very interesting one is to enforce your attacker machine, well, like a virtual machine of the attacker, to be on the same cloud machine. So that means that well, the jitter between the attacker server and the victim is very minimal. And when you combine this with using some statistical tests, it still remains possible to execute these type of attacks, even when the difference in processing time is in the order of a few microseconds. So that was direct timing attacks, and now the main focus of my presentation will be on cross-site timing attacks. So here the request is not sent by the attacker himself, but here the attacker forces the user to send a certain request. And well, because of the way the web works, the cookies to cross-origin cookies are always attached to requests. So that means that the response that is returned is specific to the user. So for instance, when the user is logged in, then he will get like a large response with the dashboard. And when the user is not logged in, the response will be small, meaning that, that would just be an error message on the page saying that the user is not logged in. So the attacker measures the time of the request and response of the victim in JavaScript. And well, by doing this attack, he bypasses the same origin policy. So I will briefly zoom in to the same origin policy because it's quite important. So it's basically the main security principle of the web. And it states that, well, a website of origin A cannot read anything from another website or in a different origin. So attacker.com cannot access anything of example.com. And well, because responses are often related to the length of a resource, this information should also be kept secret. So I will show in a demonstration later how this actually works. So this is the graph of the cross-site timing attack. So on the right-hand side, you have a social network which consists of two groups. So you have the Batman group and the Joker group. And here the attacker is like a malicious advertiser on a good web page. So here, this is our user. So this user goes to a random website, for instance, to look at cat pictures. But on that website, there's a malicious advertiser. And the malicious advertiser will try to determine whether this user is from the Batman group or the Joker group. So to do this, well, he will make the user send a request with JavaScript. So he will get the Batman resource, and because, of course, Robin is part of the Batman group, he will get back a large response. So this takes a bit over 4 seconds. Then he does the same because he wants to compare the response times for the Joker group. And because the user is not part of the Joker group, the response will be small, so it's faster to download. So it takes less than 2 seconds, which is a lot less than the 4 seconds before. So that allows the attacker to know that the user is part of the Batman group. But of course, this isn't how these things work in reality. So actually, things go over the internet using various hubs, and there's often network delays and all that kind of things. So here you can see that even for this small response, the response time is 6 seconds, which was more than the 4 seconds from before. So this is probably the reason why cross-site timing attacks have not been really exploited in the wild so far. So there are several limitations. So you have network irregularities, just as with the direct timing attacks. And of course, when you compress resources, the difference in resource size is much smaller. So it's much harder to determine whether, which one is the largest one. And of course, you can do statistical tests, but to do these statistical tests, you will need a round trip, for each measurement that you take. And in statistical tests, they only work well if you have a lot of measurements. And then another limitation is that the server that you're attacking, so the the social network with the Batman and Joker group, they might have some kind of rate limiting, preventing you from obtaining a lot of measurements. So in my research, I focused mainly on new type of timing attacks, namely browser-based timing attacks. And the interesting thing about these timing attacks is that you start your timing measurements after the resource has been downloaded. And this means that, any network delays or network irregularities don't matter anymore because you start the timing measurement after these have happened. And as a result, these measurements are a lot more accurate, And for some of the attacks, you only need to download a resource once, and then you can obtain multiple measurements, allowing you to well, very easily perform statistical tests on your measurements, because you can obtain a lot of them in a very short time interval. So this is what this new type of attack will look like. So you get the Batman request, and only after the resource has been downloaded, you start the measurements, and you measure the time it takes to process it. So processing can be seen in different forms. So you can force your browser to to try to parse it in a specific format, for instance, as a video or audio file. And we've measured the time this takes, and we found that the length of the resource is related to the time it takes to process the video, the file. Another type of attack is where you obtain it from the cache. So you can use the cache API related to the service workers API to force a certain resource to be cached, and then you can retrieve it multiple times, and you measure the time it takes to read it from the disk. And this is, of course, again related to the size of the resource. And well, the same, of course, goes for writing it to the cache. So this is a code example of how these things would look like. So you create a video element, and you add 2 event listeners to them. So first you have the suspend event, and this event will fire as soon as the resource has been downloaded. And of course, that's when you start your timing measurement. This video also has an error event, and you can listen to that event, and it will fire when the parsing is complete. So, because typically you don't want to know the size of a video, but rather of an HTML page, and HTML pages are typically no valid videos. So the video element will fire an error event because it's not a valid video. And then you set the source of the video, which will download this resource and try to parse it, and then you will measure the time between the suspend event and the error event. And a similar thing is with the cache storing attack. So there you use the new service worker APIs. So you create you fetch this resource, and once it's completely downloaded, you can start your timing measurement, and after that you try to put it into the cache using the cache API. So you clone the response and then put it into the cache, and once this is complete, you can stop your timing measurement. So then the time is related to how long it took to write it into the cache. So then we performed several of these attacks, and we wanted to measure how good they work. So on the y-axis, you can see the average time it takes to perform a timing attack. So that's in milliseconds. And you can see that here, for the classic timing attacks, for resources where the difference in resource size is less than 20 kilobytes, or 15 kilobytes, it was not possible to execute these attacks, even if you keep on sending many requests to the vulnerable server. And what's also quite interesting is that for the file where the difference in file size was 40 kilobytes, so this one here, you can see that it's missing. And that was because there was like a very brief interruption on the network, which made the time attack fail. So then we did the same experiments, but with the new types of time attacks. And you can see here the best one in purple. It even managed to differentiate between two files with a different file size of 5 kilobytes. And it managed to do this very fast, so in a few milliseconds. So this means that these new types of time attacks are really very powerful. So now it's demonstration time. So I wanted to exploit this type of attack against very popular service. So I went to Facebook, and Facebook has this functionality of Facebook pages where you can make a post and you can limit the visibility of your post. So according to certain demographics of the user. So you can limit it based on the location or the gender or the age of the user. So for instance, I can pick a post that's only visible to users of the age 26. And in this demonstration, I will try to discover the age of the user. So that's like a malicious advertiser trying to get my age that I don't want to share with them. I don't mind sharing my age with Facebook, but I do mind sharing with everyone on the web. So in this attack, the attacker first creates a bunch of Facebook posts, which are each targeted to a specific set of ages. So first, you try to discover the range of the age the user is in. So for instance, from 13 to 23, from 23 to 32, and so on. So you create all these posts, and then you make the victim fetch these posts. And when the victim is of a certain age, that makes the post visible to them, they will get a large response, and otherwise they will get a short response. And then in the third step, I repeat the process, but then I try to discover the exact age of the user instead of the range of ages. So I hope that you can see this. So here I will set up an experiment. So I will try to attack myself, and I am a user of the age 26. So I will first try to determine in which of these categories I belong. So 13 to 22, 23 to 32, and so on. So first I make myself download all the resources, which completes pretty fast. So it is less than a second to download these 6 different resources. And once these resources have been downloaded, I will perform this new type of time attack. So I will put this resource into the cache with the cache API. And as you can see already, it's pretty clear that the victim, so me, is in the age range of 23 to 32. So that's in a bit over 10 seconds that I managed to determine this. Then in the second part, I will try to determine the exact age of the victim. So there I will download the 10 different resources and obtain the cache storage time for each of them multiple times. And you can see that, well, you can see it already, but in less than 30 seconds, I managed to discover the age of the user, which, as I said before, was 26. So this works pretty well. So that's quite alarming that it works so good. Of course, we don't want this because it definitely violates our online privacy. So we will try to mitigate this, and there's two ways that this type of attack can be mitigated. So it can be prevented either on the client side or on the server side. On the client side, it's actually very hard because these timing side channels, they exist by the design of the browser. So video should parse as soon as it's as soon as possible, so the user doesn't have any delay in viewing the video. So another solution might be that you could reduce the timer resolution. So in my attacks, I used a high performance timer, so the window.performance.now method. But actually, if you have a resolution of 1 millisecond, that's already enough. So reducing the timing resolution, it's not a good solution. What might be a good solution is to disable third-party cookies, because, well, now if the attacker makes the user send a request, then the user's cookies are attached. But if so that's a third-party resource that is requested. So if the third-party cookies would not be there, then the resource would not be, depending on the state of the user, because then there would be no cookies, and then there would be no session of the user. And well, in the future, there might be a new attribute on cookies called same site, but these are still under development. So so they haven't been adopted by any of the websites yet. So we will see what the future brings. So on the server side, it's also possible to defend against these type of attacks. And there we can, we can make the observation that the cause of these attacks is related to cross-site request forgery, and we can try to defend against these attacks using the same methods. So we can try to prevent all illegal cross-origin requests. But of course, that's also very hard, especially now with the fetch API, and you can, you can hide the refer header and so on. So it's very hard to determine which requests are valid and which are not. So yeah, it's unlikely that in the near future these attacks will be prevented at a large scale. I also let Mozilla and Chrome and others know of these new types of attacks. So Firefox said that it is not an issue that they can fix on their own, and they will try to work with the people from the Chrome team to come up with a general solution. But so far they have not, and I really doubt it that they will. So when I reported this issue to Chrome, they said that it was very similar to another one called the spy in the sandbox. But yeah, unfortunately, that was completely incorrect because, the spy in the sandbox is a cache timing attack. And, the cache there is the CPU cache, and I don't use the CPU cache in any way. So yeah, they incorrectly marked it as a duplicate. So to conclude this presentation, so I've presented all types of timing attacks, and I've tried to mainly focus on these new types of browser-based timing attacks, which perform a lot better than the previous ones. So they, well, and that's because the timing measurement only starts after a resource has been downloaded, which makes that these timing attacks are much faster and much more robust than the classic timing attacks. And it's unlikely that these timing attacks will, will disappear because, well, they exist by design of the browser. So, well, it will be interesting times for our online privacy in the near future. So I've just shown the Facebook demonstration, but actually we managed to perform these timing attacks against much more web applications. For instance, Gmail, where we could read out certain contents of emails. So this means that a lot of popular web applications are actually vulnerable to these attacks today, and they will probably remain that way for quite some time because it's very challenging to mitigate this issue. So this concludes my presentation. If you have any questions, I'll be happy to answer them. And otherwise, you can reach me on Twitter, for instance.
Tom, 1 minute. We have 2 T-shirts. This is a gift for our audience for 2 best questions by your opinion. So you can give them T-shirts, by your opinion.
Okay.
Personally.
Yeah.
Hello. What kind of handling of data did you use? Some kind of correlation of measurements of time responses, or just average of large series of data?
So basically, we used the average. Well, we filtered away most of the outliers. So we draw with these. As you saw in the demonstration, we had these, what's it called?
Ranges.
Yeah. And we filtered out the outliers, and then we looked at the most probable value.
Okay, thanks.
Еще вопросы?
Hi, thank you for your talk. Very nice technique. Any plans to weaponize somehow this, like writing beef module or something like that?
Can you repeat the last part? Yeah.
Okay. Do you have any plans to weaponize this technique, like writing beef module or something like that?
Well, I didn't consider that yet. So right now, they're kind of secret, the timing attacks, but it's actually quite easy to execute them, as you saw in the code examples. Mm-hmm. So you could just use that and modify it a little bit. But I didn't want any bad people to start using these attacks yet.
But I think they have to be aware of that and be really big thing, I think, and this way people will faster, Firefox and Chrome will respond faster if this will be weaponized faster, I think.
Yeah. So far, my contact with these browser vendors, it seems that they're not very eager to come up with a solution. because currently these attacks are not being abused. So it might be useful if someone would start abusing it, so then they would be forced to fix it.
Okay.
Yeah.
Okay, thanks.
You use some parser, and basically the timing measurement is measuring the time of parsing, right, of some kind. So do you always use? You don't always use videos or video tag, right? Or what?
Well, the easiest one is the video or the audio, because it takes. Well, you also have, for instance, the image, but browsers are very fast at parsing something as an image. So for images, it doesn't work that well, but for videos and audios, it takes longer for the browser to process the whole file. So there, that techniques work best.
But why do browser parses the whole file at all? Why? I mean, isn't the mitigation just halting the parser at the very beginning, where I mean there's no video header, so the content type is wrong, right? For the web page, it's not a video.
Yeah. Well, there's one browser that I know of that does this. So Firefox stops parsing when they find that it's not a correct header. But Chrome doesn't, and I think that's because they want to provide as much as compatibility as possible. So, for instance, if there would be a video that's kind of incorrect, like if the first few bytes are not correct, and they can still manage to show something to the user, I think they really want to do that instead of saying that there's an error. So I think that's the reason why they try to parse the whole video.
So that would be a mitigation if they just disable the parser after the header is like wrong.
Yeah, but that would only mitigate against the video parsing attack. Yeah. And well, actually, there's more than just the video parsing attack. So there's the cache storage and cache retrieval, which will still work. And these are not based on any headers or information inside the resource.
Thank you.
Hello. Tom, I'm not sure that I'm right, but what happens between downloading and processing this payload? For example, if you have some third-party antiviral stuff on computer, will it also analyze this and give harm to your statistics or not?
Yeah, I haven't looked into what antiviruses do, actually, at which point they intercept traffic. But I think that it's most likely that they intercept traffic via some HTTP proxy. And then the suspend event would only fire, or the resource would be first downloaded, and the downloaded would only be complete after the checking of the antivirus. So then, this would not have any impact on the timing index.
But so you also will gain an ability to know if there is some third party or not. For example, if you send executable of the same size and I don't know, some picture.
Yeah.
So it's something like that.
But then you will need to find a web service that allows you to upload this vulnerable executable.
No, it doesn't matter. Executables are often checked. Pictures are not. Something like that.
Yeah, that might be an interesting idea to further explore.
Thank you.
Any questions? Давайте последний.
And this will be the last question.
As far as I understand, you need multiple requests to be put into cache
you put the same response into cache repeatedly. Yes?
Yes.
Then it might be possible to analyze the behavior of your program. Like, it doesn't make sense to put the same thing into cache multiple times. It's an anomaly, and so someone can prevent your attack by analyzing the behavior.
Yes, but that, well, then the browser would need to do that because, well, the browser is the one managing the cache. I think it's a possible solution. So that would help against one of these three attacks that I've shown. So the cache storage attack, but there's also the cache retrieval attack. And there, I don't think it would be an anomaly when you try to retrieve a resource multiple times from the cache, because, well, that's why the cache was made, to, well, retrieve resources from it. So it might help in defending against one type of the attacks, but I don't think it's a general solution.
Thank you.
Thank you for your presentation. Okay.